Welcome all of you. This is Dr. Sudarshan, Associate Professor, Department of Humanities and Social Sciences. I'm the faculty anchor for the SIDDHI webinar series organized by Office of Global Engagement, IIT Madras. And today's webinar will be on building integrated cooling systems for the hot and humid climate. SIDDHI webinar series is aimed at commemorating Mahatma Gandhi to create synergies for transforming India by providing a platform or a fora to discuss socially relevant technologies and bringing together various stakeholders like industry experts, government officials, policymakers, academia, entrepreneurs, think tanks, and the public. And and now I actually request Professor Raghunathan Rangaswamy, Dean of Global Engagement, to say a few words about our moderator, Professor Srinivas Reddy, who is a professor of mechanical engineering and a specialist on energy systems at IIT Madras. Over to Professor Raghunathan Rangaswamy, Dean, Office of Global Engagement.
Yeah.
Thank you.
Thank you, Sudarshan. We have run several of these webinars till now, and the idea of these webinars is both to look at socially relevant technologies and how technology affects the common man. And also, part of the idea is to showcase some of the Spark projects that we are doing. Spark projects are the projects where we have a collaborator from abroad, and the project is done jointly by both IIT Madras and the collaborator. In this case, at IIT Madras, we have Professor Srinivas Reddy from mechanical engineering, who is in the energy systems area, with expertise in that area. And I welcome you, Professor Reddy, to this.
Thank you.
And please start the webinar. Thanks.
Yeah. Thank you very much. Good afternoon. Good evening to everybody, and good morning to our friends in Canada. At the outset, I thank the organizers for coordinating this activity. I think it's a very important activity now. The Spark projects also considered as a part of this activity, and I think there's a good response for this. As far as this talk is concerned, as you know very well, that we are facing several problems, especially if you consider these problems, maybe they continue for some more time, a couple of decades. Those problems include energy, water, food, environment, poverty, terrorism and war, diseases, education, democracy, and population. Of course, these are major problems, but out of all these, the energy is most important, but we cannot address the problem of energy alone. There's a associated problem also, that is environment. But if you look at for human survival, we basically need three important things. Of course, food, water, and air. Food and water somehow we are getting by paying it, but whereas air we cannot pay for that at this time, but we are getting most polluted or uncomfortable conditions now. But apart from these basic needs, essentials, but another important thing is shelter. Shelter is very important. So now a lot of work has been done on shelter, mainly buildings. But the building now, if you look at the modern buildings, they are highly energy intensive activities, or it involves a lot of energy into the buildings. But of course, now a lot of initiatives are on for affordable households or affordable habitats. But even then, it's very important that the comfort condition is also most important. So this talk mainly on building sector, how to come up with an important aspect of building sector, mainly building integrated cooling system for hot and humid climates, mainly Indian climatic conditions. But in fact, this our association with Concordia University has been there for almost 5 years now, and we involved in the beginning on net zero energy building powered by solar energy. As I mentioned, that the Indian building sector is also consuming a lot of energy. So therefore, if we make this building sector net zero, that means without much energy, extra energy from the grid. As you know, that most of the energy is generated by fossil fuels, which again pollute the environment. So this is a very important aspect of our society. So I thank our collaborators from Concordia University for volunteering this talk. So I think it's a very interesting talk. I thank both Dr. Bruno and Mr. Nima for coming online and volunteering for this talk. Let me introduce my colleague, Dr. Bruno Lee. He is currently an assistant professor in building, civil, and environmental engineering at Concordia University, Canada. Dr. Lee joined Concordia University in 2014. Dr. Lee specializes in building energy performance simulation. His current research is mainly interdisciplinary in nature, covering various areas of building envelope, HVAC systems, renewable energy systems, and lighting as they are applied to the building as a whole. Dr. Lee specializes in building energy performance simulation. His current research is interdisciplinary in nature, covering various areas, as I mentioned earlier, building envelopes and so on. His work focuses on investigating how to better employ different computational simulations to study the performance of building environment in an integrated manner. The objectives of his research reasoning and to advance evaluation means to ensure robust design solutions that survive future challenges in dynamic environment. His current work involves applying building performance simulations, sensitivity analysis, cost benefit analysis, life cycle analysis, multi-criteria decision making, multi-objective optimization, automated design space exploration, stochastic risk analysis to different types of building environment to address various concerns. In fact, we have a good association on developing a net zero energy buildings for both India as well as Canada. In fact, Indian climate is slightly different from there, and but it's very complex. It covers almost 6 to 7 weather conditions. So, developing a building envelope for covering all these weather conditions is a bit complex, but nevertheless, it's very important for this. I also am happy to introduce another speaker, Mr. Nima Beniardi. He's a PhD student and research assistant in building, civil, and environmental engineering at Concordia University, Canada. His work is mainly related to simulation and optimization of building integrated sustainable energy system for heating and cooling. And building heating cooling is very important now. So, and mainly in Indian conditions, cooling is very important in a sustainable fashion. So now I request the speakers to start their talk, and now the forum is yours. I request uh, Dr. Leo and Mr. Nima to take over the dais. Thank you so much.
Hello, everyone. I'm Nima. I'm a PhD student and research assistant in the Department of Building, Civil and Environmental Engineering at Concordia University. Thank you, Professor Reddy, for the introducing us and your complete introduction to the topic. So today I have with me my supervisor, Dr. Bruno Lee, and also my colleague, 𝐬𝐢𝐝𝐝𝐻𝐸, who worked also in this project and he graduated recently of his master's studies. So today I want to talk about building integrated cooling systems for the hot and humid climate. And our talk has three main themes. First, I talk about the problems associated with cooling in the hot and humid climate. Then I talk about the advantages in deploying building integrated solar-assisted cooling systems. And in the end, I talk about the modeling and optimization consideration in solar desiccant cooling systems. I will also talk about the recent projects in our research center. So let's start with the first section of our presentation today. The first question is, what is the building role in clean energy transition? According to statistics, we know that building sector accounts for 28% of CO2 emission in 2017, and its emission grew more than 25% since 2000. But we have a solution, and the efficient air conditioning can reduce power capacity needs by 1,330 gigawatts by 2050, which is significant. This figure shows the world energy consumption for space cooling in buildings. As you can see here, it shows that from 1990 to 2016, the share of consumption is growing fast, and almost entirely is in the form of electricity. Also, the share of energy use from space cooling has been rise from 3% to 6%. This graph shows the cooling degree days, the mean annual average for different countries and different locations worldwide. And here you can see that Southeast Asia is one of the regions where the need for space cooling is the highest. Especially for India, as you can see here, India and Southeast Asia account for the largest share of the growth in CO2 emissions from air conditioning. And it will be in the same trend up to 2050. This figure shows the building electricity demand by end-use applications. So we have different end-use applications like appliances, lighting, space cooling. Right now, in 2016, actually, appliances have the main role, main share of end use. But by 2050, space cooling will be the single largest user of electricity in buildings. But the trend is not the same for every country. As you can see here, the countries with even higher cooling degree days, which is shown in the line, don't necessarily have the highest amount of household air conditioning systems. Even countries with lower cooling degree days have much higher number of coolings in their apartments or in their households. So, but this trend is changing, and as you can see here, from 1990 to 2017, the electric consumption of air conditioning has already risen, which is mainly due to air conditioning systems. There are two aspects when we want to consider the cooling energy demand in buildings. One is about total household electricity demand, which, as you can see here, it's rising in the left figure. But the most important point is the peak demand for cooling, which, as you can see here in Southeast Asia, it's gonna be almost doubled from 2018 to 2040. So now let's take a deeper look at what's the situation in Indian climate as an example of hot and humid climate. So here, and I also want to talk about the challenges and opportunities in this climate. So here in the figure 8, you can see different climates in India, from cold to hot and humid. And in the figure in the middle, you can see the hot and humid climate region, which is highlighted. The hot and humid climate is defined as a region which has the monthly temperature above 30 degrees with relative humidity above 55, or with the mean monthly temperature above 25 and relative humidity above 75%. And here you can see, and also here we have different cities that has been considered in this study. Chennai, Pune, that are located in that region. And here you can see the average maximum and minimum dry bulb temperature for this region. And you can see here that most of the time during the year, for the maximum dry bulb temperature is more than 25 degrees, and even the minimum temperature for city like Chennai doesn't go down 20 degrees in average. Here we have the frequency of ambient dry bulb temperature in figure 12, and you can see almost 60% of the time the temperature is more than 30 degrees, which is very significant. Another challenge or problem is relative humidity, which, as you can see again here, 60%. Relative humidity is more than 65% in almost all of the cities during the year, and this causes many problems for air conditioning. Do you hear me clearly?
Very well.
Okay, perfect. Just to make sure. So we have different conventional vapor compression-based cooling systems, which is commonly used in the market and industrialized. But they have problems getting lower because they cannot deal with humidity separately. And that causes more energy consumption to deal with that. Another problem is that they account for a large share of peak demand that I mentioned previously. And also they can have environmental issues due to leakage, which can cause problems for global warming and ozone layer problems. So I talked about the challenges. Now, what are the opportunities? We can see here in this figure that we have high solar radiation, relatively high, and also we have a high PV power potential in Southeast Asia and specifically in India. You can also see in these figures that for most of the time we have, for about 30% of the time, we have global horizontal irradiance of 750 watt per square meter, which is very significant and can be used for solar applications. And here you can see that in warm months and summer months like March, April, May, we have high solar radiation. But in rainy months in July, August, September, a little bit we will have cloud cover, and that reduces the global horizontal irradiance, which should be considered in the simulation and in the design procedure. So this building is a typical low-rise building in Chennai, and there are some challenges in designing the building. One is reducing the radiative heat gains on the roof, and another problem is to manage the high cooling energy demand in this type of buildings. But we have, as I mentioned, we have solar energy to cover the space cooling needs. And as you can see here, the solar generation has a good match with the space cooling applications, both for residential and commercial applications, which can be considered again. And here you can see the development and emerge of solar PV systems that by 2040, almost solar PV is going to rise significantly in comparison to other energy sources and technologies. But the PV system also can be developed in a way that it can better used. As you can see, the solar PV systems get heat from the sun, and the temperature on the surface rise significantly, especially in hot climates. So we can take the heat from the surface and use it for different applications. In cold climate, it can be used for preheating the building, but in cold climate, since the temperature rise significantly enough for cooling applications, the extracted solar heat can be used to be integrated to thermally driven cooling systems. So we have recently developed systems. Some of them are well working and in operation. Some of them are in research. We have absorption cooling, adsorption cooling, and solid and liquid desiccant cooling systems that can be considered. The PVT system also can be integrated with the solar air heater system to further boost the temperature of the outlet air passing through the PV system. The advantages is that, first of all, it boosts the PV efficiency and outlet air temperature, since it reduces the temperature of the PV surface and increase the efficiency of the PV electricity generation. And also it reduces the auxiliary heat source requirement and reduces radiative heat gains on the roof. And also the open sides facilitate natural ventilation. So in conclusion for this section, we found out that we need an innovative integrated solar assisted cooling system to deal with humidity and temperature and for air conditioning purposes. The system should operate with low-grade solar energy, deal well with humidity and temperature, be compatible with thermal storage systems, be feasible for Indian and Southeast Asian countries, and have easy maintenance and also reduce CO2 emissions from buildings while improving comfort and service. Now I want to go over the solar assisted cooling systems that has been used in hot and humid climates. So basically, these systems are sorption systems, and they have a process of adsorption or absorption and desorption process. And for the desorption process, we need a thermal energy, thermal heat to do the desorption. And the regeneration temperature for this purpose is varying for different technologies. For example, solar absorption systems have a relatively higher requirements, like 110 degrees. Even it can reach to 200 degrees for other materials, like SIDDHI gel relatively have lower desorption temperature requirements, but other materials may have higher. Also, we have liquid sorption materials, solid sorption materials. So it's really changing. But for our purpose, and since we want to integrate PVT system with the cooling system, we consider the solid desiccant cooling system that have a relatively lower regeneration temperature requirements. It's mostly about 70 degrees. And also we can use waste heat of solar PVT system to integrate it. And here you can see the configuration of the cooling system, desiccant cooling system. And as you can see, we have different components here. We have a desiccant wheel, auxiliary heater, collectors, sensible wheel. And also we have indirect and direct evaporative coolers. So the system works with ambient air entering the desiccant wheel, and the ambient air has a high humidity and high temperature. And when it goes through the desiccant wheel, the humidity decreases significantly. And then through the sensible wheel and evaporative coolers, the temperature is dropped and supplied to the retail store or any zone of the building, which I'm going to talk about it later. And then the return air also can be used as regeneration air for the desiccant wheel. So here we have the regeneration side, which auxiliary heater is commonly used to regenerate desiccant wheel. But to reduce the energy consumption in the auxiliary heater, we have the PVT collectors, which in the scheduled time can reduce the auxiliary heater energy consumption significantly. I'm going to talk about these results later in my slides. And also we have.
But this in chat box. Very interesting statistics look forward. I think they can hear, but I think there are no questions so far. So in chat box, so how do we ensure that India does not emit CO2 so much?
Sorry, can you repeat the question?
How can we ensure that a Indian building sector is CO2 free?
I cannot, there is a noise. I don't know why.
Or maybe others. Now, can you hear me?
Yeah, I can hear you now.
Yeah. See, there is a question that how do we ensure India doesn't emit CO2s? What are the methods to minimize the CO2 emissions in building sector?
Okay, so yeah, as I mentioned, the building sector have a very main role in CO2 emissions, especially for cooling applications. And by obtaining more energy efficient air conditioning systems, we can reduce our reliance on fossil fuels, which can consequently reduce the CO2 emissions of the buildings. So this was the main point of using solar assisted cooling systems, especially our applications, which is more related to hot and humid climates.
Thank you. That's all we have. That's all we have. There's only one question. Otherwise, if there is no questions, then we will conclude. I thank Mr. Nema. I think there's one, Mr. Nema, and so thank you. There's one more question. What is the effects on climate change? Yeah.
Solar energy in the daytime applications, but even for example, residential that usually have a different schedule, the peak demand is different from the solar energy time. So we can use storage to shift the load to the time when we don't have solar energy. And in that way, we can use the system for different type of buildings.
Okay, thank you very much, Mr. Ivan, and also thank Mr. Bruno for coming here and giving a nice talk on building sector. So, moderator can also ask. I have, I think, mainly I have one small clarification. Uh, what fraction of the building materials play a role as far as the comfort conditions concerned?
What fraction? Sorry.
What fraction of energy as well as cost are involved as far as materials of construction is concerned?
If you're asking about the cost of the system and
not only cost but also energy use, embedded energy.
About the embedded energy, we have not done research in that part yet. But about the cost of the system, I can say that about 50 or 60% of the cost is related to the desiccant wheel, and about 30% is related to the collector part, and the rest 10-20% is related to the evaporative cooling systems, and this is how it's distributed.
So what is the overall cost of the technology?
What is the rollout?
Overall cost.
Overall cost, yeah, exactly.
Cost in the sense, can it be implemented in affordable housing, or it cannot be? Is it affordable or not affordable?
The cost is really changing country to country, and the market is really different. Right now, because the system is in research and it's not yet industrialized, maybe the initial cost of the system is relatively high in comparison to other systems. But the technology is developing, and the prices will go lower. as the technology getting developed. So I don't have an exact value of the cost of the system for the different markets, uh, but as far as I know, and the research says that the technology is developing, and with that, the price will go lower.
How is it comparable with conventional uh, cooling systems like equivalent to 5 TR capacity?
The efficiency of the system is lower. As you see, the COP of a conventional cooling system is about 434, but this system has a relatively lower COP. And also the initial cost of the system is relatively higher than the conventional systems. But the important point is that the system uses solar energy to operate, which reduces the operational cost of the system. Another point is about the maintenance, that this system maintenance is also can be a challenge, sometimes with the higher humidity. Yeah, as I said, the technology should be developed further to point out these issues and solve them.
So, what is the effect of dynamic energy costs? Dynamic energy costs in the sense the diurnal variation of the energy production or energy utilization.
So as I said, we have not done a cost analysis of the system.
No. Here,
Uh,
not really cost, but what dynamic variations, like dynamic variations in the sense of how it behaves in the daytime and how does it behave in the nighttime.
oh, uh,
Diurnal variation, daily
so
variation.
yeah,
Yeah,
daily variation. Yeah.
if I can jump in for this section, the whole purpose of this research was to check the operation considering daytime schedule. So we do not the simulation that we carried out was for daytime. There's no storage, so you cannot implement this system as it is without thermal storage or without any kind of additional storage for nighttime application as of now. So the simulation is strictly for a daytime schedule of 9 a.m. to 5 p.m. for a retail store in India. So keeping that in mind, we will have to also consider the energy costs and everything.
Okay. So how can the this technology made affordable?
If you think about it, it's like any other technology. Since right now it's not so well known and not and many people use it, as Nima mentioned, it's not industrialized, so there's no mass production. So
So what are the
once
methods to make it affordable? Because I
yeah
am
so
asking these questions by the participants, same questions.
yeah, and
It's
in
not
the
from.
I think one of the questions was regarding how much is the cost comparison with a conventional system.
That was answered, but you can, if you can answer explicitly, that would be fine.
Okay, yeah. So the comparison, if you have to do, as of now, it would be 1.5 times the cost of a conventional, like a vapor compression system. The split unit that we use, it would be 1.5 times the cost of that.
Okay. But
But
what?
with
Yeah, please continue.
more penetration of this system in the industry, it can reduce the cost drastically because the major component that costs is the desiccant part of the system, which is almost 60%. All other systems are already in market in India. For example, PVT is quite cheap, quite inexpensive, and also evaporative cooling it has high penetration in Indian market, so it's also not expensive. But desiccant wheel or the desiccant material itself costs almost 60% of the total cost because it's not that widely used. So if we can bring down the cost of that, then the overall system cost will be drastically lower.
Okay. Have you done any sensitivity analysis with respect to cost?
No, we haven't done any any analysis in terms of cost. Our analysis was mainly technical and energy related, like
Okay.
operational energy cost.
Okay. And what is the typical area required to install 5 ton
Uh,
capacity?
in this case, we took I think 110 meters square, and it depends on again, it will depend on the mass flow rate that you have and the space, but this calculation we will have to do.
Okay. So how can you say that this is better than conventional system in terms of thermal comfort and also indoor air quality?
Yeah, so in terms of indoor air quality, since you have part of the air as fresh air, because traditionally these systems have been used, or these systems have been restricted to be used as 100% ventilated air, mainly because of the indoor air quality problems associated with evaporative cooling. But in this case, we tried to reach we tried to reach one equilibrium between indoor air quality, at the same time how to minimize the energy cost. So I think in this particular case, it's 20% of fresh outdoor air, which makes sure that you have minimum ventilation requirements fulfilled as per ASHRAE. So indoor air quality should not be a problem. And thermal comfort wise, we have considered strict set points for dry bulb temperature and relative humidity. And this system, I think, has 12% unmet hours as is, with better control strategy. And I think, yeah, with better control strategy, you can reduce the number of unmet hours as well. So thermal comfort wise, yes, I would say a conventional system can achieve perfect thermal comfort, like perfect conditions. But then again, you are investing a lot of energy to achieve those thermal comfort conditions, which which quite frankly, as long as you can maintain the thermal comfort at the required set points, then you don't need to invest that much amount of energy.
Okay. And there are a couple of more. You see, you have mentioned this building analysis in Chennai conditions, but I think there was one more building like some villa you must have considered, isn't it?
Uh, we did
So,
not consider the villa type system, the
mm,
building. But then again, in this case, for example, we have the low-rise four-story building, and we
okay.
are only conditioning the retail store, which is, I think, 50 meters square. So if we have to consider the villa type, then you have to do a separate
No,
analysis for the villa, because the schedule for a villa would be different. It's residential, and this is commercial, the retail store.
but anyhow, I'll add to that. Perhaps our team has considered that villa, Dr. Bala's house, and some analysis was carried out. So generally, where they're asking that where it's preferred to install terrace or some other location. Obviously, this can be integrated with the terrace easily, and it can also save some space as far as the building sector is concerned. I think it's very well integrated.
Filtration system in place. So the methodology or the design of those things will not change. You will still follow the same process. So if you are installing this system, let's say in Delhi, you would install it in any, like any other HVAC system, except the sizing will be based more on as per how you do it for evaporative cooling. Whereas in terms of conventional HVAC, it's different. But the sizing for filters and flow rates and all, it will be the same for both.
Mhm. So this minimum efficiency reporting value filters, do you use them? Or, they are. a different type?
No, I don't think I get the.
Any ERV filters are used, or some other filters?
I think it's the same as MERV. Like you use the same MERV filters that you use for typical HVAC systems.
Oh, very good. I think we have covered wide ranges of doubts and clarifications. I think I thank both of you, uh, for clarifying many doubts. I think if there are no more questions, we will conclude the session. Thank you very much for your participation, and I also thank the participants for curious questions and great participation. Thank you very much.
Thank you for having us.
Thank you,
Yeah,
Professor. Really. Thank
It's a
you.
wonderful opportunity.
yeah. We look forward to seeing you soon.
Yes,
In some
hopefully.
other days. Yeah. Thank you.
Thank you.
So,
Bye.
hi everyone. So I'm Karthik. I'm here on behalf of the Office of Global Engagement, and we thank everyone again for joining in on this webinar. Special thanks to Professor Bruno Lee for setting this up, and Professor Srinivas Reddy for moderating it. And I'm very nice talk by Nima, and the thanks to Aditya also for taking a lot of questions. I think this was quite interactive, and I thank you all for joining in. This is one of the most technical talks in SIDDHI that we've had so far, and it's nice to see the reception from the public. And we also hope that there'll be further interactions that will take place through when we upload this video on YouTube. And we also we are going to set up a new website for SIDDHI where we'll have a blog and so on. And this will finally go towards generating newer ideas and research projects and internships and so on. So I request you all to stay tuned in and continue your interaction with the panelists and so on through other modes. And we also have another webinar on 30th. So I request you to check our website for the details, and please join us for that as well. So thank you all, and have a good weekend.
Thank you.
Thank you.
Thank you.
Bye.